Good morning, everybody. Let's go over the notes on bond polarity and then on dipoles. And this will kind of help explain polar bears and penguins, the assignment we worked on. So to begin with, we've got bond polarity. And number one under this, bonds share electrons differently. And it's kind of like a tug of war for the shared electrons. Now, in the polar bears and penguins assignment, the idea was that the polar bear, being huge, could pull electrons much easier than the little tiny penguins could. And that was just an analogy between metals and nonmetals. So nonmetals pull electrons really, really well. Metals tend to give them up. Now the word polarity, and the word polarity means you've got two opposites. You know, magnets have polarity to them. They got the plus end of a magnet. Let's see if we were to, well, actually, I guess we tend to call it the north end of a magnet and the south end of a magnet. So magnets are polar, they have polarities. And we think of the North Pole and South Pole on the Earth. Well, the Earth is a giant magnet itself with a north and a south pole. We could easily call that a plus and a minus pole if we wanted to. Because we have a semi-liquid outer core that spins around, whenever you spin electrons around, it creates a magnetic field. And so we could call this the plus field and the minus. But when we say that atoms have polarity, that just means they're going to have a plus end and a minus end. Now, a couple of types. We've got nonpolar covalent. So nonpolar. Okay, so that's saying, okay, there's no, the electrons are equally shared. There is no plus or minus end. And it's a covalent, so they're sharing. And this, in the analogy in the polar bears and penguins, this would be like, if two polar bears are pulling on, I think, did they use the ice cream cones for their examples, I'm thinking? Okay, they can pull just as easily. Each of them have the same strength pulling. So, nonpolar, no charge. No charged sides of the molecule, and it's covalent, so they're sharing. And that's going to be, well, in the book it says on page 237, you take a look, the element iodine, or iodine gas, I2. Okay, it's got the same electronegativity. Those two molecules that form, when they form a molecule together, they're going to be pulling electrons equally. There is not a plus or a minus end. No, there's not. They're equally shared. Now, the other type is called a polar covalent bond, and this is where you are going to have charged ends on a covalent bond. And that's when electrons are shared unequally. So that would be the polar bear trying to share an ice cream cone with the penguin. The polar bear is going to be pulling that with a lot more strength, the polar bear being the nonmetals. Up here. Now let me zoom out a bit. So with the example of hydrogen fluoride, fluorine has the highest electronegativity of just about 4. And then you've got hydrogen, has a much smaller. Now they use these symbols, and what you saw was, in polar bears and penguins, they started drawing this arrow. And what the arrow represents is the direction of electron flow, the direction the electrons are pulled. So this is the pull direction of electrons. They're pulled that way. And when you put this little plus right down over there, that just kind of reminds us that's going to be the plus end. Now they use, in chemistry, they use these lowercase deltas. That's the Greek letter delta, which means this end is going to be partially positive because a hydrogen, when you pull away its electrons, really all you have left inside of the hydrogen is its one proton. So this side is going to be sort of positive. Now occasionally an electron does fly over here, so that's why it's sort of positive. And the fluorine is going to hog those electrons. They're going to spend more time here, and that makes it sort of negative. And I liked one of the videos I was recommending for you to look on polar bonds, the educator was talking about. He said these kind of look like S's, sort of, and he said so it's the S, that this symbol kind of, you can think of it as sort of positive and sort of negative. It's polar, meaning it has kind of a plus end and a minus end. Not like our friends, the ionic bonds, where it's very definitely you have a plus end and a minus end. You have a sort of plus end and sort of a minus end. And the electronegativity values, and I should have given you a small set of notes to put in there, which you should all have taped in. It's these right here, so you should have those taped in by now. If not, it's electronegativity chart. And also down here, when you subtract the electronegativities, it'll tell you whether you can predict a polar compound, a nonpolar compound, or ionic. And you will have to do that on the test. And that's, so what I do for number 4, I just recommend, I mean, you can write this down, or you can say, you know, see the small chart attached for figuring out what type of bond. So it says on page 238 of your textbook, that's the chart that I'd given you. I just went and copied that for you. And now I'm missing, I'm missing page, oh, there it is. Let me see, did I add anything to here? Nothing yet, okay. All right, that was part A. So just to review quickly, talked about that polarity of some of these covalent molecules, that some of them can be polar, meaning that they have a plus end and a sort of plus end and sort of a negative end. Other molecules, like the diatomic molecules, they are not polar. They're sharing their electrons equally. There's not a positive end or a negative end to it. And you can use electronegativities to, when you subtract the electronegativities of the two compounds, you can determine whether they're going to be polar or nonpolar. Part B, another term you're going to hear is dipole. Well, dipole means you've got two poles. You've got a plus and a minus. So now we're going to be talking, in that case, that's going to be polar covalent bonds will have dipoles. And the most famous one is water. So to begin with, so dipole interactions, two poles. Okay, if you like, there's a plus and minus end, if that helps you out. They occur when polar molecules are attracted to one another, and that's caused by the unequal sharing of electrons. And then here's this diagram showing hydrogen chloride. And I guess it'll take you a moment to get that written down. So we'll give you that moment. So what happens here, let me get this written down. We got hydrogen chloride. Now, this line right here, how many electrons are being shared right there? In a covalent bond, when you see a line connecting two elements, how many electrons are being shared?
2.
There's going to be 2. My memory reminder was for you, if you need to just put a little dot at the end of each of these lines, just to remind you there's a pair there. So we got hydrogen chloride. Now chlorine is much more electronegative. So it's going to tend to hog. They're going to share electrons, but chlorine is kind of like the polar bear. It's going to pull stronger. And so we get that delta shape, that lowercase delta, sort of positive, because really all that's going to be left over there is hydrogen's proton. And then chlorine will be sort of negative. Do you have a question? Okay. Now, what happens is, because this is sort of negative and this is sort of positive over here, these two can attract each other, just like the opposite ends of a magnet can attract. And so what happens is we draw a dotted line, and it usually only happens when you have hydrogen. Okay, so whenever you have hydrogen, because hydrogen is almost just an exposed proton out there, it will be weakly attracted to the chlorine over here, and you get a slight attraction. You can see this if you've ever on a flat surface put a drop of water and it does this, it beads up. because on the surface, and you add more water to it, it tends to beat up and beat up, because on the surface you've got all these water molecules. Water's a strong dipole, has a strong dipole interaction. They connect together, making like a little net covering the water. So we call that the hydrogen bond right here. So it's not a bond in that electrons are being shared or taken, but it's a bond in that there is an attraction between those. And that's, for example, the most famous one is DNA, is that the DNA double helix is held together, the nitrogenous bases are held together by weak hydrogen bonds. And when it's time for replication to occur, a big old protein can come popping through there, and the protein can just pop those apart, and then you get the double helix unwinding, as you learned last year. So, and our example here, I'm going to have you draw, let me zoom out here a little bit. Let's draw a couple of water molecules to represent that. So let me see. So we'll do, so we've got our oxygen right here, which is partially negative. We've got this is the oxygen right here. This is the hydrogen, which are partially positive. And what happens is they'll get attracted, just like I've drawn there, to the oxygen of another water molecule, which itself is partially negative. And that ends the notes right there. I've got a YouTube link I'm going to show the students in class. So with a hydrogen bond, it's just positive and negatives being attracted to each other. It's not so much a true bond. We're sharing electrons. It's very weak. So with that, let me say cut. Thank you for your attention.